Yeah, recording started. Hello, can you guys see my screen?
Yes.
Yeah, okay. So welcome. We are actually uh, we're starting the lead code practice session, and we have one easy and two medium problems to solve today. So I'll be starting with the first easy one, and this is about removing a linked list element from a linked list. So it says that remove all elements from a linked list that have a value of whatever val it is. So for example, the first example, what it says is this value val, which is 6, we need to remove all the elements who have value 6. So the value can be in the head or it can be anywhere. So if they may be duplicates also, so you have to remove each and every one. I think this is a very clear problem statement, and I don't see any other constants over here. Okay. Okay. So can you see my notepad or do I have to share it separately?
What do you mean by your notepad?
Well, okay. What do you see now? It's just the lead code screen, right?
Yes.
Okay. I'll just stop this sharing and then. Okay. Okay.
Okay. Now
Yeah, you
I
can
can
see
see
the notepad,
notepad.
right? Okay.
Yes.
So I'm just taking an example like this of a linked list, and this is a linked list which starts at 6, and then we have a few nodes here, and then it ends with a null. So the linked list is always given with a header as an entry point of the parameter in the entry function. So H stands for header. So this is pointing to the element 6. And I'm setting two pointers. One is a current pointer and the other is a previous pointer. So the current pointer is pointing to the head, and currently the previous pointer, which is the predecessor, is pointing to the null. So the way I would do is, like, if I'm given to search for a val, something like 3. So what I will do is I'll look at in the current, I will look what the value is. If it is 6, if it is not equal to the val what I want, I will just move the current ahead, and then also then move the previous position of the pointer to the previous position of the current. So here also it is not 3, so I move it again, and then I move the previous also. So the previous will keep on following it, just one element before it. And when the current reaches this 3, the previous will be at 2. And in this case, what I will do is, so I will just separate this current. I'm sorry. Okay. Just separate the current and then make the previous pointers next point to the current pointers next. And then I will delete this current pointer, but before that I will move current to current next. So it will be like this. So I'll be moving this, and now the current will be pointing to this position, and then the loop continues to the end. So that is the way of deleting a node which I'll be using when if the node is present in the mid position. But what happens if the node is present at the beginning? So if I have to delete something value of 6, which is the header, so the best way to do it will be like move the header pointer along with the current also, and then delete the 6 pointer. Like if we want to delete the 6, so we just move head is equal to head dot next, and similarly the current also, and then delete this one. So that is the only difference for doing it for the head. Okay, so any questions till now? Okay, I will share my screen again. Okay. Well, okay. So this can be it can be done several ways. Okay, the first way what I explained was I did not use a dummy node before the linked list. A dummy node is also a good option to do in that it involves less implementation. So, but this is the one I was discussing right now. So I have 2 pointers previous, which is pointing to null, and the current pointing to head, and I keep on iterating on the current pointer. And then whenever I see current value is equal to val, then I first need to identify what the header is. For that, I just see if the previous is null. If the previous is null, it means it is a header. So I just mark this to delete. This to delete pointer I'm just using to delete the pointer because I don't want to have any memory leaks. And then I just move head to head next, assuming that my value of the val is in the head. So the head also has to be removed. If it's not, okay, so when I do that, just come here, I don't increment the previous also, just move the current, and at the end I just delete this. Okay. And if it's not the head, it just comes here and then it moves the previous next to the current next, and just move the current next to the next pointer and then delete it. So this is one way of doing it. Second way is using a dummy node. So the dummy node, actually you set a dummy node which will have some value. I'm using here is like the int min. You can have any value here. And then you set the next of this dummy node to point to the head of the entry point of the linked list. And then again use the pre and cur, both of them, the predecessor and the current one. And the predecessor will be pointing to the dummy node and the current will be pointing to the head. So here in this case, when we are doing it, so we don't have to check for the head. We just check what the value is, and then we just point the previous next to the current next. So it becomes a very simple implementation. And in case if we can do also without having this previous pointer, we can just have one current also. So the way I did was for that there is some so there is only one different thing. What we have to do is first we need to actually handle the head case. If the head has a value val, so first you need to go in head, only just iterate in a while loop for the head and keep on moving it. And so if you find the head's value is that of what to be removed, so you need to delete the head, but before that you need to assign it to the next value and then delete it. And then you set your current pointer to the head, because you are sure that the head won't have the value now which has to be deleted. And then you look for current dash next is not equal to null. And whenever you come in this while loop, you actually look for the value of the next current next, not the current value. And then you can actually just point the current next to the current next and then delete it. So this can be done with a single pointer also. Hope this is clear. Any questions on this? It is a simple problem.
Yes, looks clear to me.
Okay. So do
I
we
think
want to move?
there is a. I was thinking in a different way also. I didn't try that. I think there is some other similar problem in linked list, but where we don't delete but copy the next guy value to my current value.
Okay, but in that case, if it is a tail, then there will be a challenge there to how to handle that.
What is there?
If
Sorry.
it is at the last element, if we have to do, so then in that case, actually, if you have to copy it, we don't have anything to copy there. So we'll have to handle that slightly differently.
Mm-hmm.
Yeah, but that is also a good option. Yeah, I agree.
I remember there was one question, I don't remember on my top of my head, but there it was something like that where you have to copy. There is no other way without doing a copy. But here, yes, there's a way without copy. Also, you can just remove the links and be done. But I don't remember that question. But there's a. I'm just telling, like, if in an interview you get something where you have to do something similar, then there are other, like, look for all kind of ways
Yes,
where
yes.
you just you can either delete the reference or you can just copy next guy value to current value and do something.
Yes, yeah, that is true. But only thing is if we don't want to have memory leaks or all these
Yeah.
memory issues, then it might
Yeah,
be.
and somebody put that in the chat also. Delete a specific node given only the pointer to it. Yeah, so there we have to just copy it.
Okay. So I think there is one question called the remove element or something. Or
Mhm.
okay, I don't remember. Yeah, but yeah.
Yeah, it's a delete specific node given only the pointer up to it.
Okay, okay. Yeah, maybe. Yeah.
Okay, cool.
Okay. So I'll just stop sharing and then you can take over, I think.
Okay, sure. Please let me know when you can see my screen.
Yeah.
Okay. So next question is regarding like, one
Yeah, it seemed like we don't see your screen, just the desktop.
It's only the desktop. Yeah.
because I didn't put anything there yet. Okay. Okay. So the question is to implement a try. That's it. No other way to do it. Just have to implement a try. So pretty much clear. We have to implement a try. So before implementing that, I just want to see like if everyone is familiar with try, or if they are not familiar, I will go a little bit of basic. Or if you are not familiar, you can just raise your hand so I can see like how many people are. Okay, I already got like get some overview. Okay, let's do a little bit of overview. So what is a trie? Trie is a tree-like data structure where the nodes of the tree, the entire alphabet or in the strings word can be retrieved by traversing down the branch of the tree. So basically there are a couple of things which are there in trie. You have a root, then root would have here you
वो अली पतली लग रही है हैं भैया को भी लग रही है पतली
okay. Participants, if you are not participating, yes, just
Yeah,
mute
yeah.
it. Thank you so much. Okay, cool. So trie is like a tree-like structure where you have a root and then it is followed by like 26 children and then you keep on adding. So basically if I have to add a Peter, so it would have a root, P will go there, then under P will put E, E will have T, then another E and ER. And if I have a pack, it would be similar. We already have a P. We don't do anything here. Then we go to E and then C and K. And we'll do for all the words. So can you think about a scenario where this kind of structure would be helpful? Like some kind of string matching data.
Yeah, like
Mhm.
if you have some prefix and then we have to find all the numbers which match the prefix.
Yes.
Sorry, all the strings which match the prefix, like in a
Yes.
word dictionary.
Correct. But there are two things. If I have very few numbers or like few words, then I can even do it by going through each word. But these kind of things where we have massive words, like entire dictionary, like entire Oxford dictionary or something like that, where there are so huge, so many words, and if you see this kind of structure, there are, so I try to avoid duplicate. So if P and E, they are shared, then there will be only two nodes, P and D, and then followed by there would be their child. And if two words are same, then we can even avoid duplicates in the structure. The only thing is, this will take a huge amount of memory. If you see, every root will have 26 children, and then all of them will again have 26 children. To see how the massive tree would be formed. But if our dictionary is so big, the words are so big, large in number, then this structure is helpful while traversing or finding, searching, prefix, all other things would be helpful. For example, think in that way, how Google give you that recommendation when you type some word on Google, it will give you like auto, this thing.
Autocomplete.
Autocomplete. So basically, they might be also running a try behind the scenes where your query will go. They'll try to get all kind of. For example, if you wrote PE on Google, it will go and see what all words can be found from PE, Peter, peck, pact, and other words. And then they do all other kind of logic also, some kind of a top or based on some priority geography, top search words. They do a lot of other, but the basic idea is like if you have a try-like structure, you can do all sub prefix, even word matching and other things. I think this would be more clear if I if I show you a little bit snippet, how it looks like. So what a try node would look like, I would have a map where we'll have a character, and again the value would be a try node. And then I will also have a boolean like end of word. It will say, okay, this is the end of word. And then this is a constructor. And let's say I have to insert a word in the try. What I have to do? So basically I will create a root, which will be a try node. Then what I'm doing is I'll start crawling my tree. So first a crawl will be pointing to root, and I'll see if the first character of the word is there under my root or whatever current node I'm crawling. If it is there, well and good. Otherwise, if it is null, I will create a new node there and put that character there. And if once I'm doing that, whatever is the end last node which I've seen, I've marked that as end of word.
Okay, yeah.
So there's other way of doing this. If you don't want a map here, the other way of doing is taking a try, taking an array of try. We can, and then just, yeah. We know we are only dealing with 26 characters, and then I can just create like 26 here. So this would be like an array of try. So here we have given all 26 spaces as soon as we create a node. But if we take a map, we only allocate things when we need it. But there is always an argument between taking array versus map. As soon as you take array, there is less overhead of things. You know, it's a fixed memory and a couple of other things. I think we've discussed a couple of times between map and array.
Okay. So you said try node, right, as an array, or it is try? Okay.
Oh, sorry. It would be try node.
Try
My
node.
bad.
Oh, sorry, because the class name is also try, therefore, yeah.
Yeah. So this is try node, and then the implementation in the class try.
Right.
Yeah. Thank you.
Okay.
So yeah. So there are two different ways. You can even go with the array or go with the map, whatever you feel like is okay. For example, we are talking about the try is case insensitive. So we can take a array 26 length. If it's case sensitive, then we have to make a double of size, and then we can even take a map there.
But here the try node for the array will be okay because we are dealing only with the lowercase characters. But if you have to deal with all of the characters, then I think the map should work fine, right?
Yes.
Okay.
What if you have to print like all the words in the dictionary in a alphabetical order?
Yes, that could also be doable.
Okay, then array makes more sense because hash are not ordered.
Yeah, but it depends how we are doing a hash. We can do it like a what is
You
that?
can use a tree map, but that's what, like, it depends upon the question.
Yeah.
Both choices are like equally good. It depends like what scenario you are trying to solve.
Yes.
Oh, so it means we need to be very careful whether to choose an array or a map. So we need to understand the requirement. Okay, got it. Yeah, thank you.
I mean, generally we take array when we know the size upfront.
Yeah. Based on the requirement.
Yeah.
If there is a chance that requirement may change, then changing this structure would be like changing the entire try implementation. So we have to be really thoughtful while asking the requirements. So if the person says tomorrow right now I only care about lowercase, but tomorrow the uppercase can come, that means I have to restructure my entire tree or something like that. So could be expected to ask all the clarifying questions. So let's try to try ourselves first and then see how it goes. Okay, let's do that. Okay. Can you see the whiteboard?
Yes.
Okay, let's try to, with all this theoretical things which you just saw, what we have seen, let's try to build try now. And I can't get all the controls. I got it. I'm just setting up my whiteboard. Oops. What is happening? Oh, I can't pick up eraser. Sorry, something is going weird with my whiteboard. Wait, I will
Do you want me to make?
You can use the like lead code. If you
I want to draw. That's right. Let me.
We can see it now.
Yeah, okay. Yeah, I think this is better. Something crazy happened last. Okay, so based on this understanding, what is happening? Okay, based on this understanding, we'll have something like a root. Right now, our trie is empty. I'm going to insert an apple there. What am I supposed to do?
So if it is a root, actually, if you are using an array, I'm assuming that. So I need to go to the A character index,
Which is 0.
which is 0, yeah. And then at that index, I need to actually create another trie node and assign it.
Oh, yeah, and then it would be A here. This would be a trie node, but which will be denoting to A. So basically, from roots array, I would say like this is A, and this is actually a trie node.
Yeah.
And from there, I will go to P and another P, and then L and E. For example, now I'm inserting this app. I'll go root, A is there, P is already there, P is there, so I don't need to do anything. But I have to also mark that as end of my word. This is my end of word. In the same way, I can insert a lot of things. So if I have to search something, so search and starts with a little different. I'll start with the apple. I'll say, oh, A is there, P is there, P is there, L is there, E is there. And then that node should be also end of word. If that is not end of word, then it is not a search. But if it is start with, then we don't care about the end of word.
Oh, okay.
So let's see a little bit of the solution. And then let's say meeting controls. Okay, so let's see a little bit of solution here. Okay, so we have to implement these methods: insert, search, and starts with. So if you see, I have created a trie node, which is have again a map of children, end of word, and that's how I'll initialize the hash map when the node is created for the first time, and set the end of word false. And then when I have to do an insert, what I'm doing is I'm just making crawl as root, taking the first character, seeing if it is there in the root or not. If it is not, then create a new trie node, put it that character in the root, and that node as its value, and then make that crawl as the current node. So keep on crawling. In the previous example, now we are at this node. If we are inserting apple, we are now, so now crawl is pointing to A trie node. Okay. and root would have this A as its in its children. Now next thing, and our word was now we get P. P is also not under A, so we'll just create that under A, and now my crawl is pointing to P. Then similar another P will come, then L will come, and E will come, and then the word is over. And then we set that E is my end of word. And then again I got APP. I already have, then again, I'll start with the root. I already have A here, able to fetch A because you remember if I just created, and then just point this to A. Then P will come, then another P will come, and in this case, we have not created any new trie node. And in the same way, I will set that P as my end of word. Now let's say I got another word like APC. A would be here under the root. Now it will point to A. Then P will be also there under A. When C will come, it's not there. So we'll create a new node here, put it under P, and then this guy will point to C. And we are done with the word, and then we'll set this end of word as true for at C. Is that clear?
Yeah, the insert is clear. Yeah.
Okay. So if that is clear, then even the search would be same thing. Now, let's say I want to search a word. So right now, what we have inserted in our trie, we have inserted this apple and A, B, C. Let's say I'm going to search something like A, B, C. Then I will start with this. At the root, I have A, so that is good. If I couldn't find A at my root, immediately I can return false. Because no, I can't go further. Then now my crawl is pointing to A. Then under A, we don't have any B. So that means I can return immediately false. Correct?
Yeah.
Yeah.
So now let's say we are searching a word APPL. So first A will come, under A will get P, under P will get another P, then we'll get L. Word is done, but L does not donate to end of word. So I can't say that APPL was there in my trie. So I have to return false. But say if I was having apple, then L would have E. We are going one more character, and then here it will say end of word. So that is good. So we can return true there. And let's say we are doing something here where we are looking for a starts with. So we got a word like apple or A, B, C. First we look for first we look for A, which is there. Then I look for B, which is not there. That means such kind of prefix cannot be possible. So I have to return false here. Then let's say I have APPL. I was having A, under A I got P, and under P again I got P, then under P I got L. Word is done, and then when we are out, we can just return true. So the difference is over here with between starts with or search. Here you look for in the start, in the search you look for end of word is true or not. Here we just look for true. Like we just return true, we are done with word, it is a prefix, we are good to go. So is it clear, or you want me to spend more time on this?
So go ahead. Yeah, sorry.
Yes. I have a question.
Yeah.
What if the postfix is required to search? Does it mean we need another try, or we can put prefix search and postfix in one try? Yeah, I have that question in an interview. Yeah.
So means like you want to search something like, let's take example. You got something to, so in our try I have these 3 words. So you want to search something like LE.
Mm-hmm. Yeah.
Like, okay, so what I think is what we can do is so basically try is again a tree. You can do a depth first search or a breadth first search over here, but it seems like in your requirement you want to do something like a you want to traverse the entire try and find if there is a path till leaf where you can find this pattern.
Yeah, that's the all of n search. But the requirement is how to do the postfix search, like the prefix search here.
So some other ways which I think we can do is like with every node, you can keep like how every node you can keep whatever the postfix part is left. Did you get that? So that will be additional memory, but every character or every try node will also can have, let's say, now I'm just throwing some ideas. Even I don't know how much.
Can we reverse the word and do the build another try? I mean, if you reverse a word and then or not reverse it, but build a try from right to left, and then that could help to do the postfix, wouldn't it?
No, so you're telling inserting that word, inserting the reverse word in the try?
Yes. So E first, like for Apple, you know, instead of APPLE, we will do ELPPA.
But the trick is, okay, my course, is it Emily?
Yes, yeah.
Yeah, Emily, so I think another clarification part is, do I need to implement both start and prefix and postfix?
Yeah, it's not specific requirement. I know it's just general asking how to do the prefix search and postfix search in a try. My solution is to build 2 try. One is like you in your code, it's a prefix search try. And we can build another try by using the reverse the word apple and build the try from the end to the first index. Yeah, that's my solution, but I'm not sure it's a correct answer. So
other way is that though it will take too much memory, we can insert all the prefix in the try.
So like that's a valid answer. I believe like we can create like 2 tries, one with the forward going words and one with the reverse going words. Okay, and that would work. Like from an interview point of perspective, that would work. The other approach that we can take is to build a suffix tree. It's a like different data structure, but built on top of try, which solves this particular problem for finding the suffixes. It's called suffix tree. And there is an interesting, like read about the suffix tree. but from the interview point of perspective, if you can come up with creating two tries, one with the forward word and one with the reverse word, it should be, I believe, like more than sufficient. Read about the suffix tree, and there is also interesting algorithm called Equinon algorithm, using which like you can create a suffix tree in linear time. So just by there is something called suffix tree too for this approach.
Yeah. Mm, yeah. Thank you.
Gaurav, can you pass put that algorithm name in the chat so people can copy that?
Sure.
Thank you. Okay, I think that was a interesting situation. We all might can get that in a real interview. So yeah, I think a fair answer to get started. But if somebody is still asking more better thing, then some theoretical answers like Suffix Tree could be a savior. Okay, I think that's it from my side. If you don't have any questions, then we'll move on to the next question.
I have a quick question, if it's not a problem.
Sure.
So, I mean, I solve it in a similar way, but I use it kind of like on data structure, for example. Can I show you my screen?
Yeah, but it should be super quick because.
Oh, running out of time. Okay, I mean, I can do it later on. Doesn't matter.
Or can we do it at the end? So
Yeah,
let's cover the next question and then we'll do it at the end. So in that way, people who are interested, I don't want to block it, but I want to be time bound. Sorry.
No problem. Yeah, later. It's fine.
Okay. So Santosh, I think you can proceed with the next question.
Okay, thank you. Okay, can you see my screen?
Yes, I can see that.
Okay, so this problem is again from the medium bucket. It is about like boats to save people. So what it says is there is there will be some few people, and they will have to be carried from one side of the river or whatever it is to other side, and then each person actually has a weight, and that is given as an array, and that is given as an array of integers. And a boat can carry maximum of 2 people, and it has a maximum capacity limit. So maximum it can carry 2 people. So we need to find how many minimum number of boats are required to carry all the people. And also it says it is guaranteed each person can be carried by a boat. So it means like if the limit is something about like 20 pounds, so all the weights won't all the weights will be less than or equal to 20 pounds. And just to see some of the examples here. So the first one is like this. So this is a people array which are having weights. The first person has a weight of 1, I don't know, maybe 1 pound. Okay, and the second has 2 pounds, and the limit is 3. So these guys will only need one board because they both can fit into a single board. If we add the weights 1 plus 2, it is 3. So they are equal to the limit, so that is fine. So they can just go by one board. And if we have another example here, so here actually, so you have 4 people, one is of 3, and two of them are having 2 weights and the other one is having 1. So here you can have 3 people. So it will be like a combination of 1 and 2, the weights of 1 and 2 people, and the second will be just like a 2, and the third will be carrying only the third person whose weight is 3. And another example is similar to that. If you have some array like this, 3, 5, 3, 4, and the limit is 5, you'll need 4 boards actually. So whenever there is a limit 5, so only one person can be carried, so that is one person. And if you see like 3 and 3, if we add, because they are the least ones, if we add both of them, it will be 6 and it will be more than the limit, so they can't go in one board. So 3 will have to go also in separate boards, and similar case for 4, and therefore we need 4 boards over here. And also the problem statement says that the length of this array can be maximum 50,000 and the limit maximum will be 30,000. So the maximum weight will be something like a 30,000, and you can have about 50,000 such elements in an array, or 50,000 people to be carried. So we'll have to find the minimum number of boards required to carry all the persons. So any questions about the problem statement? Okay, so
people like don't need to go in the order in that array. We can pick any 2 random, like maybe 2 or 3 random people, whatever is needed.
Yeah, so it's not a contiguous here. You can pick them in any order. That is right. So you don't have to stick to the order.
Okay.
Yeah, so the way I think is like, the first solution would be like do a simple sort first. Okay, so if I have an array, something like the second example, 3, 2, 2, 1, and the limit here is 3, I would just sort the array first, like 1, 2, 2, and then 3, and then start 2 pointers, one starting at the left and one starting at the right, and then I'll add both the values. Like now in this case, so okay, let me increase the font size now. Okay, well, I'll just share my okay. So if this is the one, so if I sort it, it will be something like 1, 2, 2, and then 3, right? So I can start with left pointer here and then the right pointer here. And then if I add both the values, it will be 1 plus 3, and the limit is, so the limit is 3. So 1 plus 3, if it is less than or equal to limit, so this is not less than or equal to the limit. So what it means that only one person of the highest weight will go through in one board. So in that case, I just need to decrement. Okay, so I need to add 1 if I have if I set a boards variable to 0. So I'll say that okay, so I will take one board for one person on the right side, and I'll just move this right person. Okay, I'll decrement the right pointer. So again, I'll compare 1 plus 2 if it is lesser than the limit, lesser than or equal to limit. So they are lesser than or equal to limit. So they both can go in a single board. So then I will just increment the board counter here, and then I decrement the R as well as increment the L. And so here, when both are on the same, the left and right pointer or on the same element, it means they need a single, there's only single person. So he will need a special board. So it will be another 3. So using sorting and then using a 2-pointer approach, this can be solved, but only the time complexity will be of O n log n. So that will be the time complexity. Okay, so is this solution clear, or you have any questions on that?
Hey, Santosh, how is it n log n? It's a log n, right?
No, I'm sorting, right? When I'm sorting,
Oh, okay.
so therefore it is n log n.
Okay, got it. Okay.
Yeah, so just, okay, the implementation is slightly.
Yeah, one more thing. Can we, I mean, put a left and right pointer on the, I mean, on the 0 itself, and just keep filling myself until and unless, I mean, I'm exhausted. Like here, for 1, 2, 2, 3, I will simply like start summing 1 plus 2, 3, right? Hello.
Yeah, sorry. Yeah, go ahead.
Yeah. For this example itself, 1, 2, 2, 3.
Okay.
I will sum up 1 plus 2. No, you can keep the right pointer there itself in the where L is right. I mean,
You mean
I
to say at the
only,
beginning?
yeah.
Both of the
I mean,
beginning? Mm-hmm.
yes. So it's like only one loop, I mean, one variable. So L and R are not required actually.
Mm-hmm.
So 1 plus 2, that will be 3, right? So here, that means these two I can put up in one bucket, like one board. And for these, I mean, for next 2, and after if I add 3 in that, I cannot do it. So these two has to be separated, right? So that would be like 3, right?
Yeah, but in that case, now this array is like that, right? So yeah, that might also work. But if we have something like 1, 1, 1, 1, 1, 1, okay, and 1, 1, so you have 2, something like 2, sorry, 2, 2, and any things, long array, a bigger array, and then you have some limit about, say, 9. So it might be sometimes if you have higher ones over here, it is always better to check with the lower one. So they both can go together, right? So you have more number of 8s here. So it is always better to fill the maximum capacity of the board first and then look for the smaller ones. Is that slightly clear, or?
Can you explain again why it not work?
No, I'm not saying it might not work, but the thing is, first, actually, you have to look for filling the complete capacity of the boards, right?
So I think
so
we
here
need to be greedy here.
Yeah. So here, if you are actually filling just one year, and then at the end, you will have to give for the 8, even if the capacity is 9, so still you will have to give them separate board over here, right?
Yes.
So instead of that, you can actually have 8 and 1 together to go on a single board. Okay, and then so you're reducing the number of boards.
Yeah, basically what Santosh is trying to say is like he's going in the greedy approach where he is finding the largest value and trying to decrease it from there. That's why he sorted out in the.
Yes, but at the end, we still need to go to every single value.
Yeah, that's true. But if you do it this way, if you try to fill the complete capacity first and then go for that. Sorry, go ahead.
So 1, 2, 2, 3, and make your limit equal to 4 and see how it works. I have to drop also, so I hope that will be a counterexample.
Oh, you mean to say for this one, right? Okay, 4, right? Okay, so in this case, so, okay, first let me do with my approach. If I say 1, 3, okay, so this will be one board. And then in the second one will be 2 boards, right? So, but if we go both left and right, so this will be 1 and 2. right? One board. And then the second one, actually, you cannot fill 2 and 3 both in the same board, right? So you'll have to have a separate board for 2 and separate board for 3. So here you will need 3 boards. And in this case, the above case, you'll need 2 boards. Okay, so that is the reason actually, yeah. So that is the reason we go it this way. Okay, but this n log n is also slightly on the higher side. That is what they say. But okay, let us quickly run through the solution first. Are you able to see the lead code screen now?
No.
Okay, just wait. Let me share. Okay. So is it visible?
Yeah.
Okay. So this solution actually is, just do a sort over here.
Mm-hmm.
Okay. And then I'm setting this left and right pointer over here.
Okay.
And it's very simple implementation.
Yeah.
As we just discussed, you have this left and right. Okay, just to be very clear, I'm just showing all these things, but it can be done. It can be optimized. The code can be optimized much better. So I'm just showing 3 conditions. If we go for this first condition, what we were discussing, if it is less than or equal to limit, you increment and decrement the right and left pointer, and then increment the board name and numbers. Or else if it is greater than the limit, you just have to decrement the right counter and increment the board. But if the both of them are on the same pointer, they just increment the number of boards and then return the boards. Okay, so but this solution is O of n. Okay, so my question is it possible to do this solution without in O of n with using some extra space? Any thoughts on that? So if you want to be more efficient on the timing, we are allowed to, it's not written in the problem statement, but we can do this solution in O of n, but without, with some, adding some more space to this. With space of O of n and time complexity of O of n, that also can be achieved. So I will just explain you the way I thought about it. So the way, okay, if we take this example again, okay, instead of, okay, this one. Okay, instead of sorting, we can do it this way. We don't need to sort. First, what we can do is we can set a weight, some array, which will be equal to size of limit plus 1. And here, first we initialize all the values, like limit is 3, so we'll have 4 elements here, initialize to 0. And now what we do is we go through this array and iterate through it. And whenever we see any element, like here it is a 3 first, so we just increment the value of 3 here, so 1. And we have the number 2 twice, so we just increment the 2 here twice. And then we have 1 here, just increment the value 1. And then we have we set 2 pointers, because the 0 index doesn't matter here. We just set the left pointer to here, and then the right pointer to here. Oh, sorry. Left pointer to the first index, and then if we set the right pointer to this index, so we do again the 2 pointer approach, but here in this case the indexes itself are the weights, and this array actually is the frequency, or maybe the number of peoples in each weight category. So
it seems like you're doing like a count sort or bucket sort.
Yeah, sort of bucket sort, yeah, but not exactly sort, but yeah, just putting them in these buckets. And then here again, you see, you always compare, like if L plus R is less than or equal to limit. So there are actually three conditions to be looked for. One is first, if the, or maybe whatever is the lesser in these two, just what do you say, you actually, you have a boat value which you have to return, which is equal to 0. So in this, the value of L and the value of R, just look for which is minimum. Here both are same. So we can always say that, increment 1, okay, the boat size, and then you make this as a 0 because you've already consumed these two people, and then decrement both these ones, sorry, move this pointer R to this place and then this one to L. So now here in this case we have 2, and the index is also 2, but if you say 2 times 2 will be 4, so it is going to cross the limit. So in that case, we know that it needs 3 boards here, sorry, 2 boards here. So we have to divide this number by 2 and also mod this number. If it is, if it was 3 over here, then we'll have to actually add, okay, first if it's 2, just add 2 here, so it becomes 3. And in case if there was an example where it was 3, so you'll have to add, actually it will be 0, 1, and then it would have been 4. So this is only a special case. So one will be actually to look for the limits, and in this you'll have to look for the first condition if L is less than R, okay, or second will be the opposite way, like L is greater than R, and the third would be if they both are equal, L is equal to R, okay. And this condition, actually when the L and both of them are at the same position, then the condition will be slightly different. Okay, so I think that if it's not more clear, I can just show you another example here. So if we have a big array like this, okay, and then we have so many people over here, and then okay, so I'm actually creating this frequency array over here. If you see, like 8 is twice, it is here, and then 7 is again twice, it is over here. So 1 is only 1. So we have some places where there are no people, so they are all zeros, right? So in this case, I start with L and R first, okay. So if I actually go by, okay, so the first thing is if L plus R is less than or equal to limit, okay, in this condition, L's value is 1 and R value is 8. So if I add 1 plus 8, which is 9, so it is not in this range, right? It is bigger than this range. So for this, what we have to do, we just have to do the same way what we did earlier. We just have to move this right pointer. But before moving the right pointer, whatever the values are in this location of the R pointer, we just have to add to the board. So there are 2, right? So I just add 2 over here, okay? And then I can make this as a 0 and just shift my R. Okay, here now I compare with L with R. Okay, when I'm comparing L with R, now I see that if 1 plus 7 is 8, it is less than the limit. Sorry, it is equal to the limit. So now I can compare whether, actually I have to compare if the value of L is lesser than the value of R. So the value of L is lesser than the value of R. So what I do is I take this value 1 and subtract from R, okay. So here 1 is left, and actually I make this as 0. Okay, and also now it is the minimum value was 1, so I added that over here. So we need actually one board to go ahead, right? So I make this as a 3, and then I keep on shifting the L till if there are no zeros over here, until I reach some value. Okay, so now when I come to L and I compare with R, so I see again now that this time L is greater, the L's value is greater than the R value. Okay, so in that case what I have to do is I have to take this R value here, okay, subtract this R value from L. So this becomes 2, and this R value becomes 0, and I actually add that to this boards over here. So this becomes 3 plus 1 will be 4. And then I shift this R pointer till I don't encounter, so till I encounter any positive non-zero number. Now in this case, both of them are 2. So what I can do is I actually can add this 2 over here. So 4 plus 2 will be 6. And here I actually make this 0 over here, and then make this 0, and shift both of them in this case. Okay, so I come to the place where actually both of them, now this is another special case where actually L is and R at the same position. So if L is equal to R position, so what for here actually I need to do is multiply L by 2, and then compare if it is less than or equal to limit. Okay, so if I do that, it means actually whatever the people are actually, the capacity of the board is 2, right? So actually if I do multiply, if it is less than or equal to 2, then I can divide these numbers and then take that number of boards. Okay, but only I have to handle the odd and even condition over here. Or else if it is greater than the limit, then it means that each person requires a separate board. Okay, in this case it is 4. So 4 multiplied by 2 is 8. So it is within the limits. So I can divide these 2 by 2. So I need a single board over here, and therefore the answer becomes 7. Okay, so and then I again increment my pointers. So it is for the exit condition, and then I exit. So is this clear or?
Yep, it is clear. It's like a great solution. Thanks for explaining this.
Okay. So I just thought I could share this, but yeah. Okay, there are some chats. Okay. Yeah, so yeah, if it looks, the implementation way is also very simple, but it is slightly more things to take care of. Here, if I look at the left and right, if they are less than or equal to limit, then I have to follow these 3 conditions over here. But this can be written slightly more efficient way also, but for just understanding purpose, I've made it separate. Left is less than right, left is greater than right, and then if they are both are the same, and here if it is greater the limit, it is greater than the limit, just we have to add the number of boards, and if they are equal at the end, we just have to take care of the even and odd length and just add the boards if it's greater than the limit. Yeah. Okay. Any questions?
I think we're good. Thank you.
Yeah. Shall I just stop the square? Okay. Yeah, no problem.
Gaurav, are you planning to take a DP session this week?
Okay, let me stop the recording.